Alright, this is a video over combining random variables, and I want you to watch this video in hopes that it helps you do your homework. Now please remember that your homework was on page, I'll write it down here in the corner in case you forgot, page 383, 22 through 34 evens. Okay, so I'm going to try to talk a little bit and then do some problems that are mimicking those problems in your homework, so it'll help you out and you'll do well. All right, the first thing I want to talk about is, remember we talked already about random variables. We talked about capital X being a random variable, and a random variable being a situation where you don't know the outcome. Okay, then we talk about mu. Remember, mu is the expected outcome for that random variable, and sigma is the standard deviation. So mu is the expected average. Remember, that's an average over the long run. It's not just a, hey, what's going to happen in 10 trials or 30 trials. It's an average of the long run, okay? And sigma here is the standard deviation, okay? So x is a random variable. Mu is the expected average of that random variable, and sigma is the standard deviation. Now, real quick, in order for us to really understand this, because some tricky, weird things kind of happen here, and you'll catch on because I'll explain it really well. But I need you to understand variance real quick. Variance is standard deviation squared. Okay, so I'm going to kind of make note of this. This is something you should definitely write down. That variance is equal to standard deviation squared. So if you take your standard deviation and square it, that's your variance. Likewise, the square root of variance is your standard deviation. So just think about that. If I square root of variance is standard deviation. So variance is a number that's used in the formula to find standard deviation, because you usually have to find variance first, and then you square root it to get standard deviation. But we're going to actually have to work with variance a little bit in this video, so I need you to understand where I get variance from. All I do is take the standard deviation and square it. That's how I get variance, okay? So let's talk a little bit about combining random variables, okay? So in class, we did this example where you have x is the number of times that the copy machine breaks in a month. So I could break 0 times, could break 1 time, could break 2 times, it could even break 3 times, or we said it could also break 4 times, and that was it. Okay, so this is a discrete random variable because there's only 5 outcomes. And then we have the probability of that. Okay, so the probability of it breaking 0 times we said was 60%. The probability of it breaking 1 time was 20%. The probability of it breaking twice was 12%. The probability of it breaking 3 times was 0.05%, or I'm sorry, 0.05 or 5%. Probability of it breaking 4 times was 0.03 or 3%. Now those do all add up to 100%. Now, in order for you to calculate the expected value. Now, usually I'm going to try to give it to you, you know what I mean, but I do want you to know how to actually calculate it. You need to multiply each outcome by its probability and then add them all together. So that would be like taking the 0 times the 0.61, and then taking the 1 times the 0.20, and so forth, 2 times 0.12, and so forth, so you can get all those, okay? So I want you to be able to hopefully practice doing that on your calculator real quick. It's really not that hard. Hopefully it's pretty easy for you to do here. I am going to, I know you see my computer screen right now because I want to pull up my calculator here so you could, so that when I do some of this stuff, you will be able to see it. So we're going to do that here. But anyway, it's very simple to do, okay? But I do want to teach you that shortcut. I talked about a shortcut to finding that and finding the standard deviation. So as soon as this opens up here, we will be able to do that, okay? So in order to calculate the standard deviation of this probability model, the first thing you want to do, if you're on that home screen, okay, is hit Stat and go to Edit. And then clear out list 1 and list 2. So highlight L1, hit clear down. Highlight L2, hit clear down, or L1 and L2. Okay, so you're going to type in those values into the list 1. So 1, 0, 1, 2, 3, and 4. And then in the list 2, you're going to put the probabilities. Make sure they match up. 0.12. 0.03 and that was 0.03. I made a mistake there. Sorry, I'm going to go up. I think that is 0.05. Okay, so there's my 60, 20, 12, 5, and 3. Okay, once that's entered in, here's the shortcut that can find your standard deviation and your mu. This is awesome. Ready? Hit stat, go to calc, and we're going to do a one variable stats. There's just one variable, how many times the copier breaks. Okay, but because we have to take into account both the outcomes and the probability, we're going to do list 1 comma list 2. So one variable stats, list 1 comma list 2, and boom, we get the average 0.71, and we get the standard deviation is right here, sigma. Look at that, 1.0516. So we're going to go over here. We get 0.71 and 1.0516. So 0.71 and 1.0561. I don't know if I did that right. Is that right? 1.0516. 1.0516. Sorry. Okay. So anyway, that is an easy way to calculate the sigma and the mu. Okay, really nicely. Now it does say x bar, it should say mu, but it doesn't, so sorry, no big deal. Okay, now let's just say that we said, okay, this is what happens 1 month. This is how many times a copier could break 1 month. What about if we want to look at 2 months? Okay, what if we want to look at 2 months? Okay, so that means we're going to have 2 random variables. Okay, we got capital X for 1 month. That's the probability, or that's the how many times it could break in 1 month. And then the second month, it could break a different amount of times. So the first thing we'll do is, well, okay, what do we expect? How many times do we expect it to break over 2 months? Well, it's really easy. The first month, we expect it to break 0.71 times. And the second month, we expect it to break 0.71 times. So just add them together. And if you need to use your calculator, go ahead, 0.71. Plus 0.71 is 1.42. So we expect over 2 months for it to break 1.42 times. That's very easy. Now, what about the standard deviation? Okay, well, unfortunately, you don't just add the standard deviation together. Sorry, you don't just do 1.0516 plus 1.0506. You don't do that. What you have to do is add the variance together first, and then square root to get back to a standard deviation. So I have to add the variance. It would be 1.0516 squared. That's the variance for the first month. Plus 1.0516 squared. That's the variance for the second month. And that would be your total variance. And then I have to take the square root of the total variance to get back to a standard deviation. That's why I was telling you in the beginning that this whole idea of variance and standard deviation is a little bit confusing. So you got to add the variances together first. Variance is just taking your standard deviation squared for each month, adding it and square rooting. So I'm going to do, now watch how I'm going to do a little bit of a shortcut here just so you could see. Not a shortcut, just less typing. Okay, I'm going to do the square root, and I'm going to do, inside that square root, I'm going to do 2 times 1.0516 squared. Now, rather than me doing 1.0516 squared plus 1.0516 squared, 2 times that obviously is the same thing. Okay, so I get 1.4872. So my 1.4872. So what that tells me is over the course of 2 months, I expect 1.42 breaks with a standard deviation of 1.4872. Pretty easy. Other than that, standard deviation is a little bit different. So hopefully that makes sense to you. So you cannot add standard deviation. You have to add the variance. Now, you have to understand that there is a difference between having 2 events or just doubling an event. Okay, so let's do some generic examples here. And there's some generic examples like this in your homework, so let's work through this real quick. Okay, let's say we have 2 random events, X and Y. I have no idea what they are. They could be how many times the copier breaks and how many times the fax machine breaks. Who knows? I have no idea, okay? And then we have the mean for X and Y. So the average for X is 10. The average for Y is 20. Again, I don't even know what these represent. This is generic, okay? And then we have the standard deviation. The standard deviation for X is 2, and the standard deviation for Y is 5. Okay, so 2 random events. Now, let's say the first example is we want to have 3 times X. Now, we're not going to do X 3 times. We're just going to triple it. So there's a difference between tripling. So when you're working with random variables, X plus X plus X does not equal 3x. There's a difference between doing the event 3 times versus doubling it, or I'm sorry, or tripling it. So be very, very careful with this. This is actually easy. So if you're going to do the event triples, you're going to triple it. You're not going to do it 3 times, you're going to triple it. What would the new mean be? The new mean would be simply 3 times 10. That's it. The new mean would be 30. Okay, again, I was working with x. There was no y. I don't have to worry about y. Okay, the standard deviation would be the same thing. You're allowed to multiply standard deviation. So it would be 3 times 2 or 6. Okay, now here's the difference. If I do it the event 3 times, if I do event x 3 times, that's x plus x plus x. I'm going to have different results, slightly different results. The mu would be 10, 10, 10. It'd be 10 for the first, 10 for the second, 10 for the third. That would be 30. So the mu stays the same, but sigma, standard deviation, changes. Here, I'm just tripling it. That's what I'm doing right here. Here, I'm not tripling it. I'm doing it 3 separate times. So this is where I have to say, okay, the first time the variance was 5 squared. Oh, whoa. Sorry, that was event y. Event x, the variance is 2 squared. Sorry. So I would have 2 squared plus 2 squared plus 2 squared. This is the variance for the first time plus the variance for the second time plus the variance for the third time. Because remember, you cannot add standard deviations. You have to add variance. So that is why it's important to understand that. Now up here, we're not adding, we're just tripling. It's a little bit different. So this is going to be the square root of, you could do 2 squared plus 2 squared plus 2 squared and take a square root of it. You get 3.46. So very, very different. Important to take note of this, okay? Or you could do the square root of 3 times 2 squared because there's 3 2 squareds and you still get the same thing, 3.46. So the sigma changes big time, okay? What happens if we add together x plus y? Okay, so we're going to add x and y. So we're going to do x and then we're going to do y. Okay, what about mu? Oh, this is really easy. X was 10 plus y was 20. Oh my goodness, how easy is this? 30. Look at that. Simple, right? What about the standard deviation? I can't add standard deviation, so please don't just say 5 plus 2 is 7. You have to add the variance. So I'm going to do 2 squared for x, that's the variance for x, plus 5 squared, that's the variance for y. I'm going to add the variance, and then I got to square root to get back to a standard deviation. So I'm going to do the square root of 2 squared plus 5 squared is a total variance, or total standard deviation of 5.39. Okay, so please make sure you're noting you cannot add standard deviations. You have to simply add the variance. Okay, all right, let's do another one here. D, let's do D. Okay, let's do y plus 6. Okay, so we're just going to add 6 to y. So we're going to say, oh, we expect 20 breaks, but oh yeah, we forgot about 6 of them, so it would be 26. Whatever, you're just going to add 6. Now, in terms of mu, this is very easy. So remember, the expected value for y was 20. Okay, if you need to go back to see it was up there, I scrolled down. And then just add 6. It'd be that easy. Remember, addition, we've learned this before, right? Addition affects the average. So it'd just be 20 plus 6, 26. However, the standard deviation would not change at all. The standard deviation would stay at 5. Done. Because addition of a constant does not affect standard deviation. We have talked about that before. If all you're doing is adding a constant, it affects the mean, but it does not affect the standard deviation, so it would stay exactly the same. Okay? Hopefully that makes sense. Now, next, this is a neat one. Ready? Let's talk about the difference between y minus x, the difference between x and y. When you're working with mu, oh my goodness, so easy. Y had a expected value of 20. Minus x had an expected value of 10. That means there's a difference of 10. Duh, 20 minus 10 is 10. That is easy. What about the standard deviation? Now, even though we're subtracting, we're not allowed to add standard deviations, so I doubt we're allowed to subtract standard deviations. But you can't subtract variance either. Anytime that you do 2 events, whether you're adding them or subtracting them, standard deviation, variance always build. So even though I'm subtracting them, when I calculate the standard deviation, I'd still do 5 squared as the variance of y, plus 2 squared is the variance for x, I still add, even though you're subtracting. That's because variance and standard deviation always build up. They never decrease. Never. So it'd be the square root of 5 squared plus 2 squared is the 5.39, the same it was before. Okay? So there's some good lessons to be learned here. Even when you're subtracting, variance, standard deviation always build up. When you're adding or subtracting a constant, it does not affect the standard deviation at all. If you're just going to triple a random variable, like right here, 3x, multiplication does affect both mean and standard deviation. Okay? So you got to be very, very careful. Let's do one more example because I really want this to make sense. And this is just a generic example. What if we had 3x plus 4y? Okay, this is going to get a little bit ugly. Okay. Let's start off with mu. Mu is really easy. It'd be 3 times the 10 for x plus 4 times the 20 for y. Very, very easy. So that's 30 and 40. Or no, I'm sorry. That's 3 times 10 plus 4 times 20. Oh boy, I can't use my calculator. 3 times 10 plus 4 times 20. That is 110. Okay? That's easy. Sigma, not so easy. Okay, the first thing you have to understand is for the x, we're just tripling. So it'd be 3 times 2. So that was a standard deviation here of 6 for the 3x. Standard deviation here would just be the 4 times 5, which would be 20. Because remember, you're allowed to multiply if you're just tripling or quadrupling. So it'd be 3 times the 2, 4 times the 5, 6 and 20. But now when we combine those, because we're combining the 3x and the 4y together with addition, we cannot add standard deviation. We have to add the variance. So that'd be 6 squared plus 20 squared. So that's the variance for the 3x's. This is the variance for the 4y's. Add the variance, square root to get back to a standard deviation. Okay? So 6 squared plus 20 squared inside of a square root is 20.88. So that's a little bit tricky. Hopefully you can use these right here to help you with some of the problems from your homework. I'm telling you that they will definitely help. Okay. All right, let's move on. Let's talk about a real simple problem. Again, this whole idea of combining things. I just want this to really make sense. And let me use a different color here. Let's say that a dozen eggs. You're going to buy a dozen eggs. Okay? And unfortunately, sometimes when you buy eggs, some of them are cracked. Some of them you open them up and some of them are cracked. So let's say that the expected number of cracked eggs in a dozen is 0.6. That's good, right? We don't even expect a full cracked egg, right? Because that's in the course of the long run, many, many dozens of eggs, we expect 0.6 to be the average number of broken ones. But of course, that deviates, and standard deviation is 0.5. Okay, great, awesome. So hopefully it makes sense. Let's say you buy 3 dozen eggs. So you're going to buy a dozen, and then another dozen, and then another dozen. How many total broken eggs do you expect? Well, that would be 0.6 times 3, because I have 3 dozen, 3 of them, right? I'm going to buy a dozen. I'm going to buy another dozen. I'm going to buy another dozen. I expect 0.6 here. I expect 0.6 on that dozen, and I expect 0.6 for that dozen. I expect 0.6 for each dozen. 0.6 times 3, that is, hopefully, that is 1.8. Expected broken eggs if I buy 3 dozen. What about the standard deviation? Okay, you can't add standard deviation. The standard deviation is 0.5 here, 0.5 here, 0.5 here. Can't add standard deviation. You have to add the variance. So I have to square those, right? Square those, get the variance for all 3, and then square root. So that would be the square root of 0.5 squared for the first dozen, 0.5 squared for the second dozen, 0.5 squared for the third dozen. So that's my 3 dozens, and 0.5 is the variance. 0.5 squared is the variance for each. Or if you want a little bit of a shorter way, you could do 3 times 0.5 squared, because that's essentially the same thing. So the square root of 3 times 0.5 squared be 0.87. So that would be my standard deviation. Okay, so hopefully that's one last problem that kind of makes it all sink in. You see how it works. Now, what do I have to assume the whole time here? I have to assume independence. So if one box has 10 broken eggs, which would be really weird, the next box cannot have any more or any less broken eggs. I expect 0.6 every single time, no matter what. Okay, let's move on and let's talk about a casino game real quick here. All right, so you're playing the casino games. This is so much fun. And when you play a casino game, usually, a slot machine, you pay $1, and usually you lose. Okay, but sometimes you might win that enormous jackpot, $100,000. Okay, so let's say that you're playing a slot machine, and on average, it pays out 95 cents. 95 cents. Okay, with a standard deviation. It takes a while to write these words here, you don't realize it. So with a standard deviation of $105. Now, the first question a lot of people say is, whoa, how could the standard deviation be so enormous compared to the average? Well, think about it. When you're playing, usually you're going to lose $1. Occasionally you might win like a $1 bet, or you might win a $2 bet, or maybe you win like a quick 5 token bet or something, okay? But, hopefully you win that jackpot of $100,000 or something, right? Now, if you think about it, the standard deviation is how much do these vary? Well, I mean, come on. Usually you're going to win very little, with the very rare occurrence that you win a huge amount. So there is going to be a big standard deviation because a standard deviation is how far you are away from the mean. Well, if I expect 95 cents, but there is a chance I could win 100,000, I mean, that is so far away from the mean. Hence, the standard deviation is going to have to adjust and be pretty large. Okay, so that's why the standard deviation is so big. So let's say that you play this game 100 times. Okay, let's say you play this game 100 times. How much do you expect to win? Well, I expect to win 95 cents every time. So if I played 100 times, that's 95 cents for each game. That's 95 cents times 100. So 0.95 times 100, I expect to win $95. Or let's think about it from the machine standpoint, because maybe I don't play it 100 times, but maybe that machine gets played 100 times. That machine expects to pay out $95. With what that would be the mu, that would be the average. With what standard deviation? Okay, well, remember, I cannot just multiply. I have to think about the standard deviation of every single play. And I'm not allowed to add standard deviation, so I have to find the variance first. I'm going to take 105 squared. That's the variance for one play. And I'm going to play it 100 times. But then I have to square root it to get back to a standard deviation. So it basically be 105 squared plus 105 squared plus 105 squared plus 105 squared plus 105 squared 100 times. Well, I don't feel like writing all those out. So I'm just going to do the variance of 1, it's 105 squared, times 100 of those, square root to get back. So it's going to be the square root of 100 times 105 squared. And I get $1,050. $1,050. So this machine expects to pay out $95 over 100 plays with a standard deviation of 1,005. Now, you may say, wait a minute, the machine, how's the casino going to make any money? Well, think about that, guys. With a huge standard deviation of $1,050, think about how much the machine could lose. I mean, okay, right? Let's think about a normal model if you really want to get into it, right? If you think about this normal model, right smack dab in the middle is the 95. If I start going up 1, 2, 3, if I go down 1, 2, 3, I'm going to be down into the negatives real quick. Because if I go 95 minus 1050, right away I'm at negative $955. And then I'm going to keep going down and down. So, a huge chunk of the time, the machine's expecting to lose money. In fact, when does it expect to lose money, right? Well, somewhere in here is $0. Somewhere in here is $0. When there's a negative, the casino's making money. Positive, I'm making the money. So if I think about the z-score for 0, right? I'm doing all the math, right? Got to minus the average divided by the standard deviation. So it'll be negative 95 divided by 1050. So somewhere down here with a z-score of negative 0.09, very small z-score right here. So the casino really is, they're not expecting to give out money. Usually they're hoping that you're going to be down those negatives losing money. Okay, because this $100,000 prize is so rare and it makes the standard deviation huge. Okay, so hopefully that problem makes sense, I hope. Okay, last problem I want to talk about is a really neat one, pretty easy to understand if everything so far is going smooth for you. Let's think of 2 bowls of cereal. Okay, so I have a small bowl of cereal and I have a large bowl. I'm going to do that a different color. Large bowl. Okay. The small bowl of cereal contains an average, or should fit, 1.5 ounces of cereal with a standard deviation of 0.3 ounces. Okay. The large bowl of cereal should contain, on average, 2.5 ounces. Again, it's a random variable. It could switch, right? It could be a little bit higher, it could be a little bit lower. So I need a standard deviation. I was supposed to be using blue here. Sorry about that. Of 0.4 ounces. Okay. Well, let's say that we pour a small bowl and a large bowl. How much total cereal would that be? Small bowl and a large bowl. Okay. Well, that's 1.5 ounces for the small bowl, plus 2.5 ounces for the large bowl. That's a total of 1.5 plus 2.5. Common sense. That's easy, even though I use a calculator. That would be 4 ounces total on average. That would be your mu. I'd expect 4 ounces total between the two bowls. What about the standard deviation? Oh boy. Okay. First off, remember this is mu, right? That's easy, right? We just did that. Standard deviation, I can't just add them. This is not how it works. You have to add the variance. That's how it works. So 0.3 squared is the variance for the small bowl, plus 0.4 squared is the variance for the large bowl, and then I got a square root to get back to a standard deviation. So 0.3 squared plus 0.4 squared, I get 0.5. Wow, that worked out nice. 0.3 squared plus 0.4 squared, square root is 0.5. So that is my sigma for a large bowl to small bowl. Okay, sound good? Hopefully that's whoa, sorry about that. Hopefully that's pretty good. All right, what about the difference? I said, what's the difference between a large and small bowl? What's the difference? Oh my gosh. Okay, ready? Mu. The difference. Oh my goodness. Come on, look. The difference between a large and a small bowl, 2.5 minus 1.5. 2.5 minus 1.5. I expect 1 ounce difference. What about the standard deviation? Well, okay. Hopefully you've learned a couple things. A, you cannot add standard deviation, so that means you cannot subtract standard deviation. However, standard deviation and variance, no matter what, build up. No matter what. So, even though I'm subtracting to find the difference, the standard deviation, the variance, always build up. So it'd still be 0.3 squared plus 0.4 squared. So it'd be the same 0.5 ounces that it was above, even though I'm looking at the difference. The same exact thing. Okay? All right. Last question of the day dealing with this, right? We just discovered that if there's 2 bowls of cereal, I expect 4 ounces. Standard deviation, 0.5 ounces. Okay? We just calculated that in the previous screen. I want to use the normal model to calculate the probability that there's more than 4.5 ounces. Okay, so here's my normal model. Right smack dab is the 4 ounces I expect there to be for the total of 2 bowls. Go up 1, go up 2, go up 3, go down 1, go down 2, go down 3. That would be, this would be 4.5, 5, 5.5, 3.5, 3, 2.5. Again, that's because my standard deviation was 0.5. So I want to find the probability of there being more than 4.5. That would be anything above that. So find the z-score. The z-score, hopefully you realize, is 1. Again, it'd be 4.5 minus 4 divided by 4. Sorry about that. Bad mistake. Divided by 0.5. That's the standard deviation divided by 0.5. So that'd be 0.5 divided by 0.5. That's a z-score of 1. I want to find the probability of being more than that. So I'd use the normal CDF, and I would go 1 more than would be 1 to 99. So normal CDF, 1 to 99. I expect 15.87% of the time I'd expect there to be more than 4.5 ounces between 2 bowls. Okay? Hopefully that makes sense. That's a way that you could link them together. Remember, to use a normal model, you need a mean, you need a standard deviation. So figure out your mean and standard deviation. Hopefully you understand all that, and rigmarole of putting them together, and how when you combine them, things are a little bit tricky. And hopefully you pay attention. Hopefully the video helped. Do those homework problems, and I know you'll do fine. Thanks, guys.